Chapter 12, Temperature and Heat. Boxes 1 through 3 cover some basic tools we need to study temperature and heat. In this chapter, the primary focus is on heat absorption. Box 1 talks about the Kelvin scale. There are 3 common temperature scales used in science. One is the Kelvin scale, another one is the Celsius scale, and of course there's Fahrenheit. Kelvin and Celsius are by far the most common scales used in science, technology, engineering, etc. The Kelvin scale is probably the most universal and most logical scale to use. The Kelvin is also one of the 7 base units, and here are the 7 base units. The Kelvin scale is based on the triple point of water, which happens at just the right pressure and temperature to allow ice, liquid, and vapor to simultaneously coexist. So if you nudge the pressure or temperature just a tiny bit in either direction, then the water changes to all ice or all liquid or all vapor. The Kelvin scale really does make sense because its 0 point is set at absolute zero, which is a theoretical temperature at which all motion stops, and that's talking about molecular motion, atomic motion, subatomic motion, everything. No vibrations, no moving of any kind whatsoever. Box 2 shows this and shows the comparison between the Kelvin scale and the Celsius scale. Celsius is pretty widely used. It's based on 0 degrees Celsius being the freezing point of water and 100 degrees Celsius being the boiling point of water. The information in box 2 is pretty important, so make sure you study it for a minute. Especially pay attention to the absolute 0 point, the ice point, and the steam point for both the Kelvin scale and Celsius scale. Especially notice the fact that 1 Kelvin, you don't say 1 degree Kelvin or 1 Kelvin degree, you say 1 Kelvin is equivalent to 1 Celsius degree. Box 3 and box 4 provide some conversion factors. If and when you need to convert from one temperature scale to another, there's your toolkit to do so. Box 5, heat. So here's a brand new form of energy. We know about kinetic energy, we know about gravitational potential energy, we know about elastic potential energy or spring energy, and most recently we learned about pressure energy. So add this to the list, heat energy. As I'm sure you're aware, heat energy moves from a higher temperature to a lower temperature, but you might not be really aware of what heat actually is. Heat really is better described by the term internal energy. Here's a good visual from hyperphysics. Internal energy refers to the combination of kinetic energy and potential energy. So think of a glass of water sitting on a table. Each water molecule is moving around with some amount of translational and rotational kinetic energy, and it also has some electrical potential energy. Everyone knows that molecules are blanketed by clouds of electrons, and those electrons interact with each other. You remember opposites attract and likes repel. So next time you look at a glass of water, stop and think about all of the different kinds of internal energy that are happening in that glass of water. When internal energy moves from one object to another, you call that heating. So we have a brand new form of energy, but the units are the same, joules. We use joules for kinetic energy and potential energy, and now we're going to use joules for heat energy. We'll also start to use the unit of calorie. Everyone's familiar with the term calories. If you look at a food label, you see the number of food calories printed on that label, which is an interesting little sidebar. 1 dietary calorie is referred to as 1 nutritional calorie, and we represent that as 1 calorie with a capital C. So a food calorie is equivalent to 1,000 calories, and 1 calorie is equivalent to 4.184 joules. Box 7, specific heat capacity. This is one of the 2 most foundational points in this chapter. Q equals mc delta T. Q stands for heat, M stands for the mass that's gaining that heat or losing that heat. C is a really important material constant called specific heat capacity, and delta T is the amount of increase or decrease in that mass's temperature. Specific heat capacity is something you look up in a table. It's a material constant, which means somebody spent some time to measure it for a whole bunch of different kinds of materials. Look at this list and notice as I scroll down, you see water. Water is very special for a lot of reasons, including the fact that it has a very high specific heat capacity. So water at 25 25 degrees Celsius, which is about room temperature, has a specific heat capacity of 4,181.3 joules per kilogram per degree Celsius. That means if I take a kilogram of water and I want to heat it up by 1 Celsius degree, I have to dump in 4,181.3 joules of heat energy to do so, which is a tremendous amount of heat. Water is very stubborn. It doesn't want to have its temperature changed. Similarly, if I have 1 kilogram of water and I want to cool it by 1 degree Celsius, I need to remove 4,181.3 joules of energy to cool it by that much. Box 8, heat and phase change. This is the second of the two major sections in this chapter. Everyone knows about the states of matter. They're solid, liquid, gas, and plasma. We need to consider what happens from a heat flow point of view to change from one state to another. How much heat needs to be added to a solid to convert it to a liquid? How much heat needs to be removed from a gas to convert it to a liquid? And all other combinations. There are phase changes between solids and liquids, between solids and gases, and between liquids and gases. Q equals ml is our defining equation. Q stands for the amount of heat, m is the mass that's being phase changed, and L is something called latent heat. If we're going between a solid and a liquid, we call that latent heat of fusion. If we're going between a liquid and a gas, that's called latent heat of vaporization. Going between a solid and a gas is called latent heat of sublimation. Here's another exciting table showing latent heats of fusion and latent heats of vaporization. Again, look at water. If I have a kilogram of water and I want to change it from a solid to a liquid, I need to add 333,000 joules of energy to do that. If I have a kilogram of water in the form of a gas, I need to remove 2,256,000 joules of energy to change it from gaseous water to liquid water. Finally, at the very bottom is a phase change diagram. This provides a lot of insight. Say, for example, I start off with just 1 ice cube of water. It's sitting in my freezer at minus 30 degrees Celsius. I take it out and put it on my kitchen table and just wait. That minus 30 degrees Celsius begins to warm up. During that warming process, we use the Q equals mc delta T equation. It reaches its melting point and it starts to melt. Notice it's flatlining in this region in terms of its temperature. That's because all of the heat coming from the surrounding kitchen is going into the water to change it from a solid to a liquid. It's breaking the bonds. For this portion of the graph, we use Q equals m times L, and that would be an L subscript F for latent heat of fusion. The heat keeps flowing in at a constant rate, and after a while, the ice is completely melted and is purely in liquid form. Heat continues to flow in from the kitchen. The water from the liquefied ice cube starts to heat up, and we use Q equals mc delta T for this part of the curve, and finally it starts to boil. And during that large flat line region that you see at 100 degrees Celsius, I have both a mixture of liquid water and gaseous water. Just like when we had the flat line region for the melting ice, I had a mixture during that flat line region of solid ice and liquid water. Finally, all the liquid water has boiled away because, again, heat keeps flowing in at a constant rate from the kitchen, and I'm left purely with steam, which itself continues to heat up.